Welcome back to American history. Today we're going to be talking about the 1776 revolution. I'm just fucking with you. We're learning organic chemistry, EAS reactions, part 1. So I know the other day you probably picked up this sheet and you're probably like, what the hell is going on with this thing? Is this pointing me to the bridge of Terabithia? Is this pointing me to a pot of gold under a rainbow? Well, no, my friends, this is actually going to be very useful for you once you figure out how to use it. And it actually shows you how all the reactions occur and what adds on and what leaves and what happens. If you can follow these arrows and actually follow the rules I'm going to show you today, you're going to be set. You're going to be golden. So moving on, the terminology you're going to need to know. You need to know what ortho, meta, and para are. So ortho I highlighted in red, meta I highlighted in blue, and para I highlighted in yellow. And that is contrary to the substituent. So if the substituent moves around, these positions are also going to move around. But for this substituent where it's located, like I said, red ortho, blue meta, and yellow para. Now, you're probably asking me, Ross, what is an EAS reaction? Well, my friend, an EAS reaction, unlike Schnorr reaction, is an electrophilic aromatic substitution that utilizes a nucleophilic carbon present on the benzene ring to attack an electrophilic molecule. But before we actually dive into that concept, we got to learn some ring electronics. So, an electron donating group, those are known as activators in EAS reactions. Now, your most common activators you're going to run into is nitrogen with a lone pair, oxygen with 2 lone pairs, or methyl or other carbon chains. Now, methyl or other carbon chains are going to be your weakest because they actually donate into the ring via adductive properties. Now, oxygen and nitrogen can actually donate that lone pair into the ring. Now, what does this mean? Why do we even care about this? Well, electron donating groups prefer to add their substituents onto ortho or para. And that's actually because of those lone pairs being donated in the ring at those positions, making it electron rich at those positions. So as you can see, when this oxygen reacts with a Br positive, you would get 2 products. You get one that adds at ortho and one that adds at para. However, due to sterics, Br is less sterically encumbered in the para position compared to oxygen, so it's going to attack at the para position. That's going to be your major product. Now, there's one exception to this rule, and that one exception I'm going to talk about right here. When you're dealing with methyl, methyl is very sterically unencumbered, meaning it doesn't really get in the way of reactive molecules. So, since it's a 2-to-1 ratio when it comes to ortho to para, the electrophilic substituent's going to attack at the ortho position because there's 2 spaces open instead of 1. So that's why that occurs when it's working with methyl. It's the only case that you're going to run into this. It's very rare. All others, when you're dealing with the electron donating groups, are going to add on at the para position. As you can see, nitrogen also adds on at the para position to make the major product. However, there are minor products at the ortho position also for both, and there is a minor product at the para position for the methyl. But overall, unless it's methyl, it wants to add on at the para position when dealing with electron donating groups. And I'll put unless meth. Oh, probably shouldn't have put meth on YouTube. So moving on to electron withdrawing groups. Now these bad boys actually make the benzene ring electron deficient. So what's that mean? That means at the ortho and para position, it's going to be electron deficient when dealing with an electron withdrawing group. But what's that mean for the meta position? Well, for the meta position, if the ortho and para positions are electron deficient, that leaves these bad boys, which I'll highlight in blue, electron rich. So what's that mean? Well, that means that electron withdrawing groups prefer to add their substituents at the meta position due to this being the most nucleophilic position. And why is that? As you can see, I showed you some resonance here that locates all the positions that are electron deficient. So, if it's electron deficient, the ortho and para position, and it's an electrophilic reaction, meaning it's an electrophile being attacked by a nucleophile, you're going to need a strong nucleophile in the ring in order for these to initiate. So it's going to prefer the nucleophilic positions on the ring, which are the meta positions. So an example, let's do a quick example just so you guys figure this out. So we have an electron withdrawing group right here. We have Br plus as our electrophile. We have our ortho positions labeled in blue. We have our para position labeled in yellow. And we have our meta positions labeled in red. So when we form this, since it's electron withdrawing group, it prefers to add at the meta position to the substituent, which is going to be one of the red positions. It doesn't matter what red position it is. There's no sterically encumbered spaces on here. So it's going to add right there. See, not too difficult. Just some easy rules to follow. Moving on. Now, halogens. These are technically electron withdrawing groups. So you'd probably be like, Ross, aren't these going to add the substituents on at the meta position? Well, you'd be wrong because halogens just do their own thing. They can either add on at ortho or para. However, they prefer para, much like the other electron donating groups. So kind of treat halogen on EAS reaction as an electron donating group, but don't consider an electron donating group because it's not. It actually has inductive properties that make it electron withdrawing. So it's going to prefer to either add here in the ortho position or in the para position. Now let's do a quick example. As you can see, we have our BR here, and para to that would be red, ortho to that would be blue, and when this electrophile attacks, it would attack in the para position. So you'd get something, well, it doesn't look like that, oh, shit, what the fuck is that? You get something that looks like this. Isopropyl down there, and that'd be your final product. You would have some minor, of course, at the ortho position, but your major product would be at the para position. So moving on. So let's look at some common types of reaction in EAS. You got the Friedels-Crafts reaction. Now, these have some problems that occur with them, and these are reactions that occur with positively charged carbocations. So basically something that looks like this, or something that looks like this, and the leaves, and then you get the same thing, which is this again. But you're going to have a reaction that occurs with one of these. It's going to be a carbocation reaction with the benzene ring. But the problems that occur with these are over-alkylation when synthesized from benzene. What's that mean? Well, I'll show you in one of the examples, but before that, you also have to watch for rearrangements that occur with these. So for example, a rearrangement. What is a rearrangement? Well, let's flex our orgo-1 muscles here, and let's think about this for a second. If I have something that looks like this. Oh shit, I didn't want to give you that because it's the exact same example problem I have down there. If I have something that looks like this, and I have my BR leave, that would then leave me with a carbocation here. However, it can gain stability by doing a hydride shift, which would shift that hydrogen down here and make this your new carbocation. And that's now ready to attack because the tertiary carbocation is the most stable carbocation you can possess. So let's look at some examples of these. For this one, this is just regular benzene, and when the iodine leaves from the methyl, it would make Me+, and when that attacks, it would make this. However, this is when an over-alkylation occurs, because this molecule is actually more reactive than this molecule. And when you're actually doing organic synthesis in the laboratory setting, you have to remember it's not just one molecule reacting with another molecule, it's millions of molecules reacting with millions of molecules. So you still have millions of these guys in your solution. So what's that mean? That means they can keep attacking, and now that you have a methyl on here, that is now an electron donating group, meaning it can now have this, it can now have this electrophilic methyl attack at the ortho or meta position, which is here or here. So it's just going to keep attacking since there's millions of these guys still around. So you're going to get this, and then you'd probably get either this, or you'd either get this. And it would just keep adding on, because you have it add in the ortho position first because of that one rule with methyl where it actually it doesn't really care about sterics since it is so sterically unencumbered. And then the methyl would add at the para position then, because it's just going to keep over-alkylating unless you actually keep doing a reaction with another thing, such as, say, you instead put a second step into this reaction to actually solve over-alkylation. Which, say now, instead of that, we just want to fix this. We'll then react it with Br2, FB, Br3. So then we can actually figure this out, which would then be this. That's a skinny benzene, but you see where I'm going with this. You could then form that. However, if you just keep it in the solution with the other methyl electrophiles, it would just keep adding like I showed you previously until you actually add another step into the reaction. So that's over-alkylation. That's what that is. But let's ignore that and let's look at the next example. Now this is where that rearrangement comes into play, because when this iodine leaves, it forms a primary carbocation here. However, it can get to a secondary carbocation, which is much more stable via hydride shift, which then moves that guy here. So then when it actually attacks, you're going to have this as your compound. And once again, Br is one of those weird halogens that actually prefers para. So that's once again what you'd get. Because since it does prefer para, it would add the carbocation on at the para position. So moving on to the next type of reaction you're going to run into. You're going to run into Friedel's Kraft I spelled that wrong. It's called acylation, not accutation. I don't know what that is. I think I created a new word with this. But that is not what it's called. It's called acylation. Apologize about that. Now this is an addition of a carboxyl with various substituents attached. So how do these work? Well, if you have a normal benzene ring, what happens is the chlorine leaves, and then you get the intermediate, which would look like this. And then it attacks. Well, since it's just a benzene ring, it can attack anywhere. So, since there's no electron withdrawing group or electron donating group on here, we can just tack this bad boy on. And I'm going to attach it on here because that's an easy place to attach them on. Now then, let's go a step further. I just want to think about some things here first. 2 ortho positions. 2 meta positions, a para position. Now what do we do here with this reaction? We added on an electron withdrawing group. So now say if we went on to synthesize something different, this now plays a role in where that would add. Say we added on a Br, it's going to actually add on here. I'm not going to show a reaction arrow, but say I wanted to add Br plus onto this reaction I just showed. Where would it add on at? It would add on at the para position or the meta position because it's an electron withdrawing group. So it's going to add on here. If we did end up having a reaction that involved Br plus. But since we don't have a reaction that involves Br plus, this would actually just be your final product. But I just want to show you that because that's what we're going to get into with these. This is going to lead into synthesis. Synthesis is reaction after reaction after reaction forming a specific type of benzene ring. But first you have to learn all these different types of reactions before you can just start adding stuff on and the rules. Now for the next one, the same thing's going to happen here. Cl leaves, and then it just attacks that benzene ring. And it's going to attack anywhere I want it to attack since its benzene's equally rich everywhere. So I'm going to attack it at the top this time. Since there's no electron withdrawing group or donating group on here, the electronics don't even matter. It's just a benzene ring, so it can attack anywhere. But I'll attach it there. And that's how these work. So what's the next one? It's called nitration. What does nitration do? It adds an NO2 group on. So when we do this, HNO3 and H2SO4 is the reaction arrow you're going to usually see when this occurs. And all it does is it adds, sorry I have to draw these out, on an NO2 group. Now once again, if we kept synthesizing this, we now have an electron withdrawing group on here, so now it dictates towards the meta positions. You see how these are working? Next reaction is called halogenation, and all it does is add either Br or Cl onto the benzene ring or the other ring with other substituents on it. Depending on the substituents, it's going to determine where it adds on at, but we're not onto those examples yet. We're just looking at the reactions overall. So for this benzene ring, here's what I'm going to do. Here we go. Work smarter, not harder. It would add on a Cl onto the benzene ring. And now, once again, we have a halogen on here, so it's going to prefer ortho or para. Preferably para for the major product. KMNO4. What is KMNO4? Well, KMNO4 reduces carbon chains on a ring to a carboxylic acid. So how's that work? Say you have a methyl here, and it's reacted with KMNO4. All that happens is, I'm gonna draw my benzene ring out. The methyl just turns into carboxylic acid. Or the carbon chain just turns into carboxylic acid. Same thing for this. Next one. They just turn into carboxylic acids. No matter how long the chain is, it just gets replaced with a carboxylic acid. And there is one exception to this rule, though. The exception is terbutyl cannot undergo this. If you see terbutyl, it cannot react with KMNO4. And if you look on your chart, you'll see that also. It just doesn't work that way. So if you have terbutyl on there, it will not be replaced with carboxylic acid when reacted with KMNO4. So moving on. There is a side note about KMNO4. Say you have a non-benzene ring or you have OH attached. KMNO4 turns it into a double bonded oxygen. That's what it does if there's OH present. It's the one side note about KMNO4. ZnHG with HCl or PDH2. These remove the oxygen double bond from the molecule. So, unless it's on, I will show you a little example on that also. When it's on a benzene ring, it removes the double bonded oxygen. So what's that look like? Well, basically, this is all that happens when you see this. Say you have a double bonded oxygen. It just gets reduced, leaving you with a carbon chain. Now the side note about this is, if it's not on a benzene ring, it turns into OH. That's the only side note. Pretty simple. It's on your chart, but I just want to show them out. Now, that we know all the reactions and how they work, and I hope you have your chart on you, let's do some practice, guys. Let's figure these out. Let's really get these nailed into your head. So, what's the first problem we have? We have HNO3, and as we know, this is nitration. Look on your chart for it. We also, however, have an electron donating group. So it's going to prefer to add ortho or para. Due to sterics, it's going to add that group para. One second, I'm going to do something so I don't have to draw all these out. No, actually, wait, I forgot. There we go. Okay, it's going to add it para. And that would be your final product. Your final major product. Of course, there'd be some minor product at ortho position. For the next one, what's going to happen? Well, you have an electron withdrawing group right here. And we're reacting that with Br2. So if you find Br2 on your chart, you'd see that it adds a Br. So where's it going to add it at, though? That's all we have to really know. Since you have the chart, you know what it adds. You don't have to memorize all the different additions that's going to occur on the benzene ring. You just have to know what the electronics of the ring actually are. Since this is an electron withdrawing group, it's going to prefer to add at the meta positions. That's not, the second one's not meta. The meta positions. So you would get this. That would be your final product. For the next one, once again, another halogenation. However, it's got methyl on here, so it's going to come down to some statistics. Even though it can add in the ortho or para position, since it is methyl, methyl is sterically unencumbered, so it's going to add at the ortho position. 2-to-1 ratio, baby. Here we go. And then you got CO. And you got methyl, and then you got this. And that's how that one works. So moving on to some more complex ones. So we have OH. Now, is OH an electron withdrawing group or is it an electron donating group? Well, it's an electron donating group. So we can actually add at the ortho or para position. Now what's going to happen here? This leaves, make this positive, and then it's going to attack at the para position. So you're going to get a molecule that looks like this. So for the next example, what is going on here? This looks like a double benzene ring. Well, it's aromatic, so it will perform an EAS reaction. However, we have an electron withdrawing group over here. What's up with that? Well, my friend, don't even worry about it because it's not even going to be able to donate into the ring or withdraw from the ring. You just completely ignore it. The thing we want to worry about is this oxygen right here because you have to remember there's 2 electron pairs on this oxygen. And those can actually donate into the ring, meaning that it's going to favor either ortho or para, and due to sterics, it's going to attack para. It's less sterically encumbered at para. So, let me do this because I don't want to redraw this thing. And once again, it's a halogenation if you look on your chart with Br2. So it just adds Br at the para position to the electron donating group. The next one, let's look at this. What happens here? What's significant about this? When this leaves, it forms a carbocation that is primary. Now, a rearrangement can occur via a hydride shift. So when this hydrogen shifts over, it will make a more stable carbocation at the tertiary position, which is right here. Now let's analyze our benzene ring. We have a halogen, so it can either add ortho or para. However, due to sterics and reactivity, it's going to prefer para. So when we draw this out, or when we copy and paste, because Ross is lazy, we would get a product that looks like this. And of course, you'd have some minor product at the ortho position. So those are